Okay, welcome to GADEPS. So today we have Bruno Klingler, who is going to talk about, maybe I have to make bigger this typical and
atypical intersections.
Atypical intersection
in Hodge theory. Yeah, so I did prepare with my handwriting, which might not be perfect, but I hope this will be readable. First of all, thanks a lot for inviting me to speak here. It's a pleasure. So what I want to talk about today is a general problem about detecting Hodge cycles. So let's give a motivation first. So suppose you start with a smooth family of algebraic varieties of a field. So here S is quasi-projective over K, and the morphism F is, let's say, smooth and maybe even projective for simplicity. And then the goal would be to describe the motivic locus. So what do we mean by this? We mean that we want to consider the set of points in the base S, such that in some sense the fiber is simpler than the very general fiber. And here what we mean by simpler is basically that the motive is simpler, and this means that the fiber XS, or maybe its powers, contain more algebraic cycles than the very general fiber and its powers. Okay, so this is what we would call the motivic locus of the family, right? And it's kind of easy to see, if you have a good theory of motives, that this motivic locus is a countable union of irreducible algebraic subvarieties of the base. And those irreducible algebraic subvarieties, they are called the special subvarieties for your morphism. Okay, so this is kind of an abstract description. Maybe let me give the first example, some examples. So everything I will talk about will be over the complex numbers. And the first example is kind of very easy. So we look at the modular curve. And here I will cheat a bit because, of course, this modular curve, if you want to be rigorous, it's rather a stack than an algebraic variety. But let's just cheat and suppose that there is a universal family over it, which means that I'm putting some level structure in the background, but I just don't want to remember this. So the family I'm considering is the universal family of elliptic curves over the modular curve. And this modular curve, from the complex analytic point of view, and even algebraic, this is just C, right? Thanks to the J function. So here, the parametrization, the complex parametrization is that if you have tau, which is a point in the Poincare per half plane, then you can associate to it a curve which is C modulo Z plus tau Z, right? And this is your elliptic curve. And then you see that this J function is very transcendental, but it will identify your modular curve with C, so it's kind of easy. And now, what does it mean that you have exceptional algebraic cycle in the fiber, or maybe in some powers? Well, for instance, you can look at the endomorphism of the fibers, and it's well known that generically this is Z, but there are some points where you have more endomorphism than just the trivial ones. And in that case, the endomorphism of your elliptic curve are just an order in Q of tau, exactly when tau is imaginary quadratic. And so this means that if you look at this family, what I call the special points, the points where the fiber has exceptional algebraic cycles, these are exactly the CM points, right? So they correspond to the points J of tau, where tau is imaginary quadratic in Poincare per half plane H. So one remark is that this collection of points is dense in C, just because imaginary quadratic numbers are dense in H. So when I say dense here, this is even for the usual topology. So a second example is a generalization of that one, and you can look at the family of the universal family of principally polarized abelian variety of genus G. So there is curved AG, which is this this moduli space, and this Gothic AG, which is the universal family. And again, you are interested in the motivic locus. So you are looking at the set of points in curved AG, such that the fiber has more algebraic cycles. Or when I say the fiber, maybe some products of those fibers, and so on. And in particular, it contains various things. It contains, first of all, the generalization of the first example. So, namely, the cases where the abelian varieties, which are the fibers, have exceptional endomorphisms, and so many that you correspond to CM points. So, where the abelian variety has complex multiplication. And another example of points in this motivic locus is the locus where your abelian variety splits up to isogeny into a product of a dimension k times a dimension g minus k variety. Okay, so you have this locus AGK inside AAG inside the motivic locus of this family. So this is a second interesting example, and maybe a third example is let's consider for your basis S the locus of smooth surfaces of degree D in P3, where D is a positive integer, and then over S, well, so this S is an open subset in a projective space corresponding to your linear series. And, well, you have the universal family of such surfaces over S. And now this is a standard result of Noether that for D at least 3, a general surface of degree D has pKa rank 1. So the pKa of your surface is generated by O of 1. Yeah, here, of course, there is a Z somewhere. So it's rank 1, which means exactly that every curve on such a surface of degree D is a complete intersection in P3 of your surface with another one, right? Now, the motivic locus for F would contain what is classically called the Noether-Lefschetz locus, where you are looking at surfaces of degree D where the rank of these pKa groups becomes bigger. And again, it's kind of easy to see that this Noether-Lefschetz locus is dense in S, even for the usual topology. So now, are there any questions at that point? I hope what I'm talking is kind of clear, but please interrupt me if there are questions.
Yeah, it's okay.
It's okay. Okay, so now I will turn to the Hodge incarnation of this kind of problem, because we don't understand much about algebraic cycles. And so in some sense, what we do is that we linearize this problem. So I replace the algebraic variety XS, which is the fiber of my family, and an algebraic cycle in it, just by its cohomology in a certain degree, even degree, and the corresponding Hodge class of this algebraic cycle. So, and now I replace my family X over S just with the variation of a structure over S. Okay. So in general, I can consider even variation of mixed structure on S, which have to be admissible. And then rather than studying the motivic locus for F, the Hodge incarnation of that problem would be to consider the Hodge locus for this variation of a structure. So if you have a variation of a structure of V, then you can look over a quasi-projective base S, then you can look at the Hodge locus that denoted by HLS V tensor, which means that I look at all the points in the base where when I look at the fiber, so the fiber VS now is a certain Hodge structure, and I look at the points S where this Hodge structure has exceptional Hodge tensors. So it has more Hodge tensors than the very general fiber in your variation. And this is this locus that I'm interested in. So now, let me talk now a minute about general results about these Hodge loci. So I will restrict myself for simplicity to the pure case, which means that if you think in the geometric situation, I'm considering the case where my map F is proper, and then I remind you a few basics about Hodge theory. I guess most of the people in this seminar are very familiar with that. But suppose that you start with a finitely generated Z module. Then what is a Hodge structure on that Z module? This is there are three equivalent definitions, basically. Either you think of it as a Hodge decomposition on the corresponding complex vector space. So decomposition into pieces VPQ, such that VPQ bar is VQP. Interestingly, and this is the point I will consider here, is to think of this as being a representation of C star seen as a real algebraic group inside GLVR. Right? A representation of C star is just of C star seen as a real algebraic group. If you look at the corresponding complex vector space, this gives you a representation of C star cross C star, which is a complex group associated to that C star. And so this gives you the backgraduation. And the fact that this is defined over R, this is what gives you this symmetry VPQ bar is equal to VQP. And thirdly, a third way of thinking of Hodge structure is in terms of the Hodge filtration rather than a bigraduation. So the Hodge filtration, of course, is related to the bigraduation by taking FPVC as being the direct sum for R larger than P of the VRS. And conversely, VPQ then in that case is VP intersected with VQ bar. Okay. So now let me remind you what I called Hodge classes. Well, they are just the rational classes which belongs to V00, or equivalently the rational classes in F0, or equivalently the fixed point under this representation of C star in VQ. And then a very important invariant of your rational Hodge structure is its Memphotic group. And so what is this group? Well, there are various definitions of it, depending on your presentation of what a Hodge structure is. And this Memphotic group will be, if you want, the Zariski closure of a Q of the image of this Deligne morphism. So you take the image of C star inside GLVR, and you look at the smallest algebraic group that contains this real co-character. So this will be a reductive Q algebraic subgroup of GLVQ. And it happens that with this definition, this is also the fixator in GLVQ of all the Hodge tensors appearing in all the tensor power of VZ and its dual. So VZ tensor here denotes the direct sum of all AB of VZ tensor A, tensor VZ dual tensor B. Okay. And so this means that the more Hodge tensors you have for a Hodge structure, the smallest Memphotic group you get. Okay, so this is order reversing. All right, so with this reminder, I still also need to remind you that everywhere in what I will be talking about, there is a polarization in the background, which is a bilinear form on my Z module that satisfies certain positivity property, the Hodge-Riemann relations. And of course, the basic fact is when X is smooth projective, then its cohomology in degree I will admit such a functorial Z Hodge structure of weight I. Okay, so now I was talking about variation. So what is a Z variation of Hodge structure? Well, this is an interesting guy. So you get first VZ, a Z local system of finite rank. And then you look at the associated complex flat bundle, and you look at it as being a holomorphic flat bundle. Then you ask that so this is curved V and nabla, and you ask that this guy is a filtered DS module when you consider the Hodge filtration. And finally, the last piece is the polarization, on which I don't want to insist. And the requirement is that at each point of the base, then if you look at what this triple gives you restricted to that point, then you get exactly a polarized the Hodge structure in the previous sense. Okay, so I guess everybody is still familiar with that. So are there any questions? Or is that okay?
Yeah, for me, it's okay.
It's okay. Okay. So of course, the typical example is in the geometric case I started with. If you have a smooth projective morphism, then your local system will be just, for instance, if you work in degree 2p, it will be R2p f lowest star of z. So this will be a local system where the fiber will be the cohomology of the fiber of f in degree 2p, and with z coefficients. And your D module, your filtered D module will be, well, the holomorphic bundle, which is in fact algebraic, will be this R2p f lowest star of the relative Durham complex and endowed with the Gauss-Malin connection. And the Hodge filtration on this R2p f lowest star will comes from the stupid filtration on omega x over s.
Maybe I kind of have a question.
Sure.
Actually, it's a kind of historical question. I know that it's a kind of a classical, but why the people has, starting from Griffiths, has fixed one cohomology and not considering the cohomology ring? Is there
yeah, I think, well, in some sense, I think this is because, well, it depends what you want to do. I mean, you see, in my case, I want to take the tensor, I want to take the tensor category generated by this thing. And I think, intuitively speaking, it's not clear geometrically what happens if you mix, right? I mean, when I would take, if I consider the entire ring, and when I take the tensor, then I will mix the pieces one with the others. And I guess geometrically, people were not so confident. What is the meaning of this? It's not completely clear, right? But I think it's just historical. It's just, I don't know why people did choose to fix the P rather than just taking the direct sum. And of course, you can take the direct sum. It does not change anything.
Okay.
What I will say. All right, so now what is the Hodge locus of such a variation? Well, this is exactly what I said. You look at the set of points in S where the fiber has exceptional Hodge tensors. And with my interpretation in terms of Memphotic group, this means that the Memphotic group is strictly smaller than the generic one, which means, in some sense, which means equivalently that dimension is not maximal. And then, if you think about it, it's not at all clear what is the structure of that Hodge locus, because Hodge theory, in some sense, is kind of transcendental, right? You are looking at the interaction between the rational structure coming from the Betti cohomology, and then you are looking how it interplay with the F0, your Hodge filtration, which comes from the Durham side. And so this set that you have defined, it's not at all clear that it has any nice geometric structure. However, if you believe in the Hodge conjecture, then this Hodge locus should coincide with the motivic locus that I defined, which is defined in terms of algebraic cycles, and which was obviously algebraic, at least countable union of algebraic stuff. And so the main result in all this game is a theorem of Cattani-Deligne-Kaplan that says that unconditionally, without the Hodge conjecture, and in fact for any variation of a structure, not necessarily coming from geometry, then this Hodge locus is a countable union of irreducible algebraic subvarieties of S and algebraic subvarieties of S that I call the strict special subvarieties of S for this local system. So the picture that you have to that you need to have in mind is that each time you have a variation of a structure, you get for free this countable union of irreducible algebraic subvarieties. And of course, inside those ones, you have those of dimension zeros. These are the special points. And inside the special points, you have very peculiar one, which are even more special, which are the CM points. and which correspond to the case where the Memphotic group at that point is a torus, so the smallest possible reductive group, a torus. Okay. So you have to think that on each of those special subvarieties, there is a generic Memphotic group that becomes smaller and smaller if the special subvariety becomes smaller and smaller. All right, so this was the presentation of the Hodge-Locke, and now what I want to say is there is something remarkable when you do Hodge theory is that this Hodge-Locke can be thought as intersection loci. Just a parenthesis is that you could try to do the same thing studying, for example, Lie cyclic sheaves and Tate classes rather than Hodge classes. But the situation is much more complicated because you don't have this interpretation of this Tate loci in terms of intersection theory. And the reason is that in Hodge theory, you have period maps, while for L-adic sheaves, you don't. So let me try to explain this. If you start with a variation of Hodge structure over your base, then for each point, what you want to parameterize is really the position of your Hodge filtration at the point S inside the locally constant sheaf that you have with generic fiber I call VC. So you just want to parameterize the position of the Hodge filtration, right? Or equivalently, you just want to parameterize this co-character corresponding to this Hodge filtration. And so naturally, when you have a variation of a structure, you get a period map, which is exactly the map parameterizing this Hodge filtration or this co-character equivalently. So what is this map? Well, first, this will be a complex analytic map because the Hodge filtration has a remarkable property to vary holomorphically. Okay? And it would take value in what? Well, if you argue locally, it takes value in some flag variety, right? And now it will not really take value globally in a flag variety because there is some monodromy when you come back to a point following a complicated loop. Then, of course, you have the monodromy of the local systems that play a role. And the second remark is that it will not really take value in the full flag variety because there is a polarization. And this is where the polarization plays such a crucial role. It tells you that, in fact, you will arrive in some open subset of your flag variety that I denoted here by D. And in fact, this D is just a conjugacy class of the generic Memphotic group for your variation of a structure. And so this is what is called a flag orbit inside a flag variety. And the group gamma by which you take the quotient is an arithmetic subgroup in this generic Memphotic group. So why is so something interesting happens here is that insist that in general this picture is completely complex analytic, right? It's well known that in general, except if V comes from weight 1, basically, D mod gamma has no algebraic structure at all. This is not an algebraic variety. This is a complex analytic manifold, but not algebraic. Of course, when you are in weight 1 or some special cases in weight 2, D mod gamma is what is called a Shimoa variety. This is an algebraic variety, but in most cases, it does not admit any algebraic structure. And so really, this period map is purely complex analytic. It's not algebraic. So this is what makes Hodge theory so funny to study. All right, so what are the properties of that period map? Well, as I said, this is holomorphic because the Hodge filtration varies holomorphically, and this is horizontal. This means that you have to satisfy the certain PDEs equation. So these PDEs correspond to exactly to this relation that I showed here, which is there, that the flat connection is very constrained. It has to shift the Hodge filtration by at most 1. So, which means that the differential of the period map, which is exactly describing how the Hodge filtration is varying, tells you that it is very constrained. It has to lie, in fact, in a very special subtangent space of the tangent bundle of D mod gamma. All right. So now let's try to interpret the special subvarieties in terms of this period map. So you start with your period map here, and now what I'm saying is that inside this quotient of the period domain, there are many, countably many beasts of the same kind, which are also quotient of smaller period domains. Okay. So here I tried to make a picture. On the right, you have ds mod gamma s, and inside ds mod gamma s, you have a very regular submanifold, which is dy mod gamma y, which is smaller. And now what I'm claiming is that the special subvarieties are exactly the preimage under the period map of this dy mod gamma y. So you see that understanding Hodge loci, this is really understanding this intersection of the image of S under this holomorphic map with dy, all the dy's mod gamma y. Okay. So this is what is summarized in this blue line. A special subvariety is exactly the preimage of such a guy. And now this is interesting for many reasons. The point is that when you have an intersection problem, there is a notion of the intersection problem being typical, which means that you are in general position, or atypical, which means that you are not in general position. And this leads to very different problems, in fact. So I will say that a special subvariety Y in S is atypical if this intersection problem is not typical, which means that when I try to intersect the image of S with dy mod gamma y, then this intersection is not transverse. So on my picture, I made an extreme case where dy mod gamma y was in fact contained in the image of S. So, of course, the idea is that such atypical intersection should be rather rare, right? And so there should be rather few atypical special subvarieties. So at that point, this understanding Hodge loci in terms of intersection theory, you have a few natural questions that come into your mind after looking at Cattani-Deligne-Kaplan result. The first one is to try to describe the distribution of these special subvarieties, right? I mean, you know that you have countably many, but a basic question, for instance, is what can be the Zariski closure of this Hodge locus, of the union of all those special subvarieties? Can we say something about that? And a second question is, can we say more if we restrict ourselves to the atypical locus? So the locus where, in fact, the special subvarieties where your period map has excess intersections with those dy mod gamma y in the image. Okay. So this is the kind of question I want to address now. And well, a few years ago, I made a conjecture, which is a generalization of well-known Zilberpink conjectures for Shimura variety. And basically, it says the following, that if you start with a variation of a structure, well, you can forget about admissible and graded polarizable. This is for the mixed case, and let's focus on the pure case. Then, in fact, there should be only finitely many maximal atypical subvarieties for V. This means that if you restrict yourself to the special subvariety which have an excess intersection, and you take their union, well, in fact, they are contained in finitely many maximal ones. Okay. So, as I said, if you are in the very special case where your period map is takes value in a Shimura variety, and let's say that the period map is immersive. So in that case, S is just a closed subvariety of your Shimura variety. Now what you are trying to do is intersect S with all the Shimura subvarieties up to equicorrespondences. So these are exactly the special subvarieties inside Shimura. And then such an intersection will be, I consider only the atypical ones. And then this conjecture is exactly what is standardly called the Zilberping conjecture.
There is no restriction on S. I mean,
so here I'm taking any algebraic subvariety of my Shimura variety.
Okay.
Okay. And
can you remember what was the maximal when you say?
Maximal, I mean for the inclusion. Right, you see, I mean, special subvarieties can be included one into another, right? And then what I'm saying is that if you take all of them, and I take their union, in fact, all of them are contained infinitely many maximal ones.
Okay.
Okay. So a typical application of this main conjecture is what I call the Andrew-Hart conjecture for variation of Hodge structure. So this is an extreme case of atypical intersection. So suppose you have a variation of Hodge structure, and suppose that you restrict yourself to the special subvarieties which are mapped to Shimura subvarieties inside your period domain, and such that in restriction to those special subvarieties, the period map is dominant. In other words, what I'm looking inside S of all the special subvarieties which are essentially Shimura subvarieties. And then the claim is that if such a collection of Shimura subvarieties inside S is Zariski dense, then this is possible only if S was essentially already a Shimura variety, in the sense that the original period map was dominant onto a Shimura variety. Okay, so in particular, it says that if you have a variation of Hodge structure that contains a Zariski dense set of CM points, then this means that the period map has to be dominant onto a Shimura variety. So this is very restrictive in terms of arithmetic. So what is happening with this? So I could spend a lot of time trying to explain the conjectures, but I prefer to move to some results now. So let me explain some results that I obtained with the first one. Theorem one is with Odvinovska. So I start with a pure variation of a structure, and I will make a simplifying assumption because I think it makes things easier to explain. I will suppose that the generic Memphotic group for this variation is simple. So I am not in a product situation. I just have one simple group, at least if I take the adjoint group. And now, if I look at the Hodge locus, as I said, this is a union of special subvarieties. And of course, the most difficult pieces to understand are the points, which are isolated. And so I will rather consider only what I call the positive, the Hodge locus of positive period dimension. So in other words, I take the union of all the special subvarieties whose image is not a point, but is really positive dimensional inside the period domain. And then, surprisingly, is that we can completely describe the distribution of such a locus. So we don't understand the distribution of special points, but we understand the distribution of the positive dimensional components. And there are only two options. The first option is that this Hodge locus, which is a countable union, is in fact on the nose algebraic, and it's just a finite union of special subvarieties. In other words, again, this means that all the special subvarieties of positive period dimension, they are contained in finitely many maximal ones for the inclusion. So this is the first option. And the second option is that if it is not the case, then it is Zariski dense. So there is no intermediate situation. You can imagine that this Hodge locus concentrate in order to be Zariski dense in a strict subvariety of S. But what I'm saying is that this is just not possible, except if the Hodge locus on the nose was already algebraic. So maybe let me describe a simple corollary of this, which was not known even for Shimura varieties. So suppose that you take a subvariety of the moduli space of principally polarized abelian variety of dimension G, which is Hodge generic, meaning that the generic Memphotic group of S is the same as the one on AG. So namely, this is the general symplectic group. Now look at the intersection of S with all the Shimura subvarieties of AG and keep only the components of positive dimension. And then the claim is that either this is a finite union of special subvarieties, so this is algebraic on the nose, or in fact, this intersection is Zariski dense in S. Okay? So it really describes quite striking result, I think, about the distribution of the of these intersections of positive dimensions. So there were previous results of Colombo, Pirola, and Isali and Chai that were saying that okay, if S is sufficiently big, so namely if the codimension of S is smaller than G, then in fact this Hodge locus is even dense in S for the usual topology, not only for the Zariski one. So you are automatically in the second situation, and you are dense even for the usual topology.
So in the case of surface in P3, it says that if it's not...
I'm coming to it, so this is the next slide.
Okay.
I know I did not write it. So in the case, you get exactly the same result in the case of surfaces for P3. So if you take it tells you that this, if you have a subfamily inside this moduli space of surfaces of the gradient P3, and if you intersect with your special subvarieties there, and you keep only the positive dimensional, I don't know what happens for points, but if you keep only the positive dimensional subvarieties, then either this is algebraic on the nose or this is Zariski dense. Does it answer your question? Yes?
Yeah, I think, but you said the next slide. You are going.
No, I was thinking I wrote it, but in fact I did not write it because I decided to. Yeah, I'm sorry. I should. So this is the same kind of result as here.
Okay.
Exactly the same.
Is there an analog of this result in yellow also? If the codimension is small enough? Yeah.
Well, basically, the analog is that I think it was known only for the full S that I described, namely for the full modular space. Then it's well known that the Noether-Lefschetz locus is dense by itself, even for the usual topology. But I'm not aware of result for subvarieties of that modular space of sufficiently small codimension. Probably it should be possible. You see, I mean, this is, you have to check this green criterion. This is the proof of the density for the usual topology is quite different from what I will explain. I mean, this is really a differential geometry. You are just and so this is infinitesimal argument. So there is this green criterion that tells you that you get a submersion somewhere, and I don't think anybody really tried to write the analogous result to this one in yellow. Okay, so a second result that I did put into quotation mark because is that it's not written yet, is a result with Baldi and Ulmo, where basically we prove this Zilberping conjecture for the positive locus. Namely, take a variation of Hodge structure, and here I think that to be precise, I forgot to assume also that the generic Memphotic group, the adjoint of the generic Memphotic group is simple. So here it should be added. And now let's look at the special subvarieties of positive period dimension, so the ones which are not mapped to points in the period domain, but consider only the atypical one, so the one with excess intersection. And then the claim is that you prove the conjecture, namely this is the finite union of special subvarieties. Okay. And so this means in particular that we prove André Hort, but not for CM points, only for positive dimensional special subvarieties. So suppose you have a variation of a structure, and suppose that this S contains a union of positive dimensional Shimura varieties, basically. This is, of course, you have to be more precise. I mean, special subvarieties of Shimura type, meaning that the period map in restriction to the special subvarieties takes value in Shimura variety and are dominant. But let's say summarize by saying that S contains Zariski dense collection of positive dimensional Shimura subvarieties. Then S has to be of Shimura type itself. So basically, S is an open in a Shimura variety. So this is the content of this corollary. So again, you see that what you are missing are the interpretation of the points. And so just to make a comment, it's kind of natural. I mean, all the techniques that we use are essentially geometric and variational. So we need to have some families. So we need the image to be positive dimensional. For points, it seems that the question is much more arithmetic and delicate, and I don't want to talk about this today. So what do I want to do now? I want to try, yeah, I'm just repeating, I'm going over my head. Yeah, I wanted to nevertheless say something about arithmetic. So as I said, we say nothing about special points, but let's turn now to the case where S and the variation are both defined over Q bar. So for instance, suppose that you start from a family of algebraic varieties defined over Q bar, not only over C. And then the same heuristic that was saying that the special subvarieties should be algebraic, it would tell you that not only they should be algebraic, but they should be defined over Q bar. Okay. In fact, this is implied by much weaker conjectures than the Hodge conjecture, namely the conjectures that Hodge classes are absolute Hodge, which is, if you want, roughly the half easy part of the Hodge conjecture. You don't need to have an algebraic incarnation by algebraic cycles, but just that the Hodge classes are absolute Hodge. And then with Odvinovska and Urbanik, we recently proved that still under the assumption that the adjoint group is simple, then any special subvariety of positive period dimension and which is maximal for this property is actually defined over Q bar. And again, this tells you that as soon as you have some geometric information, namely that the image is not just a point, then we can say something. And of course, the case of points seems much harder. And in fact, the case of points is essentially equivalent to the fact that Hodge classes are absolute Hodge. All right, so this was just a parenthesis. I won't say anything today about that, more than stating the result. So what I want to explain rather is to try to give an idea of what kind of method we use to prove this kind of stuff. So as I said, forget about, well, you should emphasize here, I'm interested only in the proper case. So the result is really due to Baker and Zimmerman. And it was a result that I conjecture in the same paper in 2016. This is a result in functional transcendence. And recently I extended this with Gaut to the mixed case. And there is an alternative proof by Chu, a student of Jacob Zimmerman, to extend to the mixed case. So, what is the kind of method that we use? We use a result in functional transcendence. So suppose you start with a variation of a structure. And so you have this period map, which is here from S to D mod gamma. And let's look at the universal cover of D mod gamma. So this is just D. So now we use the fact that D is embedded inside, is an open inside a flag variety. And so this makes sense to think that D has some natural algebraic structure. Namely, I will call an algebraic subvariety of D just the intersection of an algebraic variety of D check with D. Okay, so now what is the functional transcendence statement that I have in mind? Well, it is saying that this period map has a strong relation between, establish a strong relation between the two algebraic structure on the quasi-projective variety S and on the algebraic structure on DS coming from the embedding in the dual period domain. Namely, let's take the fiber product of this diagram, and I call it delta. Okay. So delta is kind of a strange beast. I think of it as being an algebraic variety. Of course, it is not, strictly speaking, but this algebraic variety takes into account the algebraic structure on DS, the algebraic structure on S, and the transcendence of the period map phi S. Then the statement of this actional result kind of statement tells you that if you take a closed analytic irreducible subvariety in delta, then what I can do is I take the Zariski closure of this closed analytic subvariety inside this guy, which is algebraic on the nose. And what it says is that I control the dimension of this Zariski closure. Namely, the dimension of the Zariski closure minus the dimension of Z has to be at least the dimension of the smallest weakly special subvariety containing the projection of Z in S. So weakly special is a variant of special. You define special in terms of the generic Memphotic group, and you can give exactly the same definition, replacing the generic Memphotic group by the algebraic monodromy group, which is a smaller subgroup. So this is the first ingredient. So the simplest ingredient you have to think is the following. It tells you, suppose you start with something which is algebraic in DS, meaning that this is an irreducible component of something algebraic in this DS check, so a flag variety with this open subset DS. Now, take the preimage of this in the universal cover of S by the lift of the period map, project it to S, and take the Zariski closure. Then this statement that you have here tells you that automatically the Zariski closure of something algebraic in DS projected to S has to be weakly special. So this is an extremely strong statement that constrains a lot the geometry of this diagram and tells you that this map phi S has a very good transcendence property, in fact. The second result that we use is a result due to myself and Becker and Zimmerman and Brunbarp in the mixed case that tells you that the period maps, although they are not algebraic, in some sense they are very close to being algebraic, namely they are definable in some O-minimal structure. So an O-minimal structure is a generalization of real semi-algebraic geometry. So this is a tame geometry where all definable sets have very good topological properties. For instance, they have only finitely many connected components. So basically, what it says is that if you want to write explicitly this period map, then you can do the following. You can find a finite atlas of charts for the analytic manifold associated to S, and a finite atlas of charts for DS mod gamma S, such that when you write this map in those atlas of charts, then you can write it using only the real exponential map. This is the meaning of this exp. So I insist, the real exponential map, not the complex. The complex is bad because it's sinusoidal, so it's not tame. So the real exponential map and real analytic function restricted to compact sets. Right? So I repeat, this is what is the meaning of that statement. I think this is extremely important, is that it tells you that if you can find a finite atlas of charts on both sides, such that when you write this map in these atlases, then you can entirely write it in coordinates using only the real exponential map, the full real exponential map, and real analytic functions, but restricted to cubes, basically, to compact sets. All right. So, it seems that. So now let me try to give an idea of the proof of Theorem One. So I remind you what Theorem One is. The Theorem One is saying that if I take the special subvarieties of positive period dimension, I take their union, I take the Zariski closure, then either this Zariski closure is the entire S, or in fact, I was already algebraic on the nose. So I didn't need to take the Zariski closure, and I had only finitely many maximal special subvarieties of positive dimension. So how do you prove such a thing? Well, the first thing is to really make a picture. So you have this variation of a structure over S. Then what you can make a picture of the horizontal leaf going through a class lambda in this bundle, right? So V of lambda will be the flat leaf of lambda. And inside V of lambda, I can try to describe what is Vi of lambda. So this is the intersection of my flat leaf with the Hodge subbundle of degree I. And all this Vi of lambda will project onto something that I call Si of lambda, which is just its projection inside S. So if you do the case I is equal to 0 and you take a rational class, then you see that what you are looking is exactly the locus in your bundle where the flat transport of your rational class is a Hodge class. So this is exactly the locus of Hodge classes you are interested in. And S0 of lambda is the locus of points at which one determination of the flat transport of lambda is a Hodge class. And so for general high, you just have a generalization of this picture. But what will be crucial, and this is the main new idea in the proof of Theorem One, is that you don't want to argue directly on Hodge classes, but you have to argue on any complex class. So the remark is that, in general, if you do not start with a rational class, then V of lambda and Vi of lambda are much disgusting objects, in the sense that, okay, if you think of them as being subspaces in the étalé space of your flat bundle, then this gives them a natural complex analytic structure, right? They are just analytic subsets of the étalé space. But certainly inside V, they are not complex analytic subsets. Okay, and so the geometry of those Vi of lambda and of its projection Si of lambda for general lambda is just disgusting. And this comes from the fact that lambda can have an orbit under the monodromy which is dense. So there is no way Vi of lambda will be nice enough. Okay, so it's just a disgusting set. But what I claim is that nevertheless we understand a lot about the closure of that disgusting set. So there are two ingredients in the proof of the theorem. The first ingredient is, okay, let's take a Vi of lambda. So this is the locus where lambda is in the I space of my Hodge filtration. And now fix an integer d and consider only things in this locus of local dimension at least d. So this is again a disgusting set, but what I'm claiming is that you can consider the union of all those things for all possible classes lambda. And here I take lambda with non-trivial monodromy. So this is the meaning of this NT, to be precise. Okay, and then I can look at the projection of that set. So Vi of lambda larger than d is disgusting, and I'm taking a union of those disgusting sets. But the surprising result is that, in fact, this union is on the nose algebraic. So I think this is this is a statement that tells you that, in some sense, something which looks a priori very transcendental when you restrict yourself to one class, to such an extent that this Vi of lambda is not even a complex analytic set. When you take the union of all possible lambdas, then it's very nice. In fact, it's on the nose algebraic inside FIV. And the main point is that this has nothing to do with Hodge theories. It's just a property of flat algebraic connection. So the theorem is that if you start with a flat algebraic connection and you take an algebraic subvariety f, so here in our case this would be fi, the ith piece of the Hodge filtration of the total bundle. Then if you look at fixing a point in this f and looking at the set of points in X such that the union of the intersection of the flat leaf with f through X as at least dimension d, and taking the union of all such X, then this is algebraic inside F. And the proof is basically differential geometry. I'm really using here the flatness of the connection and parallel transport to prove this. So what happens? The corollary of this is a kind of saturation result. It tells you that, suppose now that I take the rational classes and I look at the locus where those rational classes, when I transport them flatly, then they stay in the ith piece of the Hodge filtration and they drawing something of dimension at least d in this horizontal leaf. Well, the claim is that when you take the Zariski closure, then in some sense, this set stays saturated by the Vi of X for points X, which are not anymore in VQ, but in VC. More precisely, you saturate that guy. There is an open subset, Zariski open subset in this Zariski closure, such that it is contained in the union of all the leaves Vi of X of dimension at least d, and still contains this Zariski closure. So the second result, the second piece for proving Theorem One is that now that I have this result, I can also just study the Zariski closure of a single Si of lambda. So I project to S, and I take the Zariski closure of this Si of lambda. And the result is coming from the functional transcendence statement that I mentioned, is that this guy has no choice, but it has to be weakly special. And the reason is that this Si of lambda is exactly of the kind I described at the beginning. It's coming from something algebraic in the period domain, G. Well, the result that you get from Theorem B and corollary A is that if you look at this locus, I recall you that we are interested in S0, which will correspond to the Hodge locus. And if I consider the projection of this Vi of VQ of dimension at least D, then this is saturated by weakly special subvarieties. So this is a permanence property. I start with things which are related to special subvarieties. If you think of the I is equal to 0 case, I take the Zariski closure, and then when it will still be saturated, maybe not by special subvariety, but by weakly special subvarieties. So with this, let me try to indicate briefly in the last 2 minutes the proof of the Theorem One that the Zariski closure of the positive Hodge locus is either the full S or it is the Hodge locus by itself, positive Hodge locus by itself. So without loss of generality, we can assume that the period map is immersive. This is not a big deal. And so now what we are really looking, this positive Hodge locus will be with the notation above this S0 of dimension at least 1. So I'm really looking at the locus where the projection of the intersection of my flat leaf with F0 is of dimension at least 1. So here there is something interesting happening, which is due to a finiteness result of the link that tells you that in fact, rather than studying this infinite dimensional variation of a structure, because here I'm taking really all the tensor powers, you can consider only finitely many. So in other words, the Hodge loci will appear in bounded tensor degrees. This is what it means. And so without loss of generality, I can suppose that I'm not really considering a tensor power, but just the original local system itself. It does not change anything. So we are back to our previous situation. All right, so now when I'm here, the corollary B will tell me that the Zariski closure of my positive Hodge locus will be saturated by weakly special subvarieties of positive dimension. But now, what are these weakly special subvarieties? As I said, they are intersection of the image of the pyramid map, not with special subvarieties of D mod gamma, but with weakly special ones, which are more general, but of the same shape, D prime mod gamma prime. Well, and then, because of this saturation property, you can just analyze at what is the geometry of those weakly special subvarieties. So there is one trivial case where this weakly special subvariety will be the full S. But then this tells you exactly that this Zariski closure, which contains this leaf, which is a full S, has to be S itself. And in the second case, this means that for all point X in this Zariski closure, the leaf, the weakly special YX, is strictly contained in S. Now, the important result here is that under the assumption, this is the only place where I use this assumption, under the assumption that the generic Memphotic group is simple, the geometry of weakly special subvarieties tells you that necessarily the weakly special subvariety is contained in a special one, which is also strict inside S. But then you see that on the one hand, the Zariski closure of the Hodge locus contains the Hodge locus, and this Hodge locus will contain the U because this Hodge locus is the union of those YX, and each of them is contained in the WX, but WX itself is already in the Hodge locus. But then you see that the Zariski closure has to be equal to the guy on the nose by an easy Noetherian argument. And then this means exactly that this Hodge locus was itself a finite union of maximal special subvarieties. And this finishes the proof. So you have this alternative. So I guess I have to stop here and not talk about the other result with Ulmo. The only thing I want to say, I want to summarize by saying that this crucial fact that Hodge loci really can be understood in terms of intersection loci makes all the richness of that topic and all the nice property of this intersection either typical, like the result that I proved with Odvinovska, or atypical, like the result that I proved with Baldi. And then the main methods are basically coming from a tame geometry and this result that I mentioned, which is that these period maps, they are transcendental, that's true, they are not algebraic in general, but essentially the only difference between a period map and an algebraic function come from the real exponential. And although the real exponential might be frightening to an algebraic geometer, in fact, this is a very tame function. If you think of a function like exponential minus 1 over x, this is a very nice function that converges very well, and you should not be, this is a tame function in any sense you can give to the name tame, and one should not be frightened by them. And in fact, all these result in Hodge theory, I think in the background, they have this kind of, they come from this kind of tameness properties. All right, okay. I think I will stop here.
Okay, thank you, Bruno. So let's thank the speaker. Okay, any question? I have my own question. Let me see, Ananio, Roberto, you are.
Yeah, I had a question.
Okay,
so,
Ananio.
Yeah, so I wanted to ask that if I take in the case of hypersurfaces in P2n plus 1,
yes,
and I take a general one-dimensional family, parametrizing yes. Smooth hypersurfaces, so I think I should go. So I start with I fix a smooth hypersurface of degree d, and I take a one-parameter family which has this variety as a special fiber.
Yes.
Then if I look at the Noether-Lefschetz locus in this one-dimensional family,
Yes.
Is this going to be dense as well, or is this going to be a finite number of points?
Okay, so you see, I mean, if you restrict yourself to points which are atypical, then the conjecture tells you that it should be finite. And this I cannot prove. So for instance, if you look, so the conjecture would be, for instance, that if you look at CM points on that curve, then you should have only finitely many. Because CM points are automatically atypical as soon as you are not working in a period domain, which is a Shimura variety. So, for instance, if you are interested just in CM points, then yes, there should be only finitely many. But now, if you think that those points are not atypical, so you see, I mean, this curve, you have to think that it will give you special points intersecting possibly special subvarieties of complementary dimension. So those ones would not be atypical. And then you can perfectly imagine that they are dense. So, but all right. So now after that, what I have to say is this is really, each time you will have this kind of question, the question will be reduced to knowing if you are in an atypical situation or a typical one. But what I want to emphasize is this is not an abstract question. I mean, this is really a question about existence of special subvarieties of sufficiently high complementary dimension. So if you work with a curve, it's very unlikely that there will be a special subvariety in the period domain which is a hypersurface. So most probably all intersection will be atypical, and then the conjecture would tell you that you have only finitely many points in all cases. Of course, there are exceptional examples where you have period domains where you have period subvarieties which are hypersurfaces, but they are very rare, even in Shimura varieties. So,
is there a prediction on the largest number of points that can?
But this I think is a very interesting question, but it's much more refined. So it will depend on the arithmetic nature of the points. If you work with CM points, then I think it should be feasible to have to make predictions depending on the degree and the complexity of the CM points you are considering. But as I said, in the general case where you are not working with Shimura variety, it's not even clear that those CM points, and this is the content of the conjecture that Hodge classes are absolutely Hodge. It's not even known that those CM points correspond to Q-bar points in your original family. Okay. So basically, although there should be a lot of conjectures to be made, I mean, first you have to solve the fact that Hodge classes are absolute Hodge, even to give a meaning to those conjectures, because otherwise you don't even know that those CM points are Q-bar algebraic points if you think in terms of the original Q-bar algebraic structure on your variety. So I think we are basically completely stuck with points. I mean, because except in the case of Shimura varieties, we can say very little. So for instance, this is also an example that I should have mentioned. I mean, if you think of the simplest possible family of Calabi-Yau threefolds, right? Just the dual quintic. So you have a one parameter family. And there, of course, this is a very famous question to know if there are infinitely many or only finitely many CM points on that family. But the main problem is that you don't even know that the CM points should correspond to Q-bar algebraic points in P1 minus 3 points, which is in fact your curve. So this is very embarrassing. I mean, even the basic questions, you don't know how to be in a setting where you can say something meaningful. So maybe I should, maybe I should also answer your question by looking at that example. That example is quite interesting. If you look at the question, look at this one parameter family through the quintic mirror, quintic, the Calabi-Yau threefold mirror quintic. If you are asking what are the points where the Calabi-Yau structure in degree 3 splits non-trivially, then this is a typical intersection problem, and there should be infinitely many points. But if you ask how many points are CM in this family of Calabi-Yau threefolds, then the conjecture is that there are only finitely many, and this is a typical difference between atypical intersection on one hand, corresponding to the CM case, and typical intersection corresponding just to a splitting of your Hodge structure as a direction, a non-trivial direction.
Thank you.
I think I will ask my question in the non-recorded session. So let's, I think nobody wants. Okay, let's move to non-recorded session. Just a moment. Stop recording.